So today we'll be looking at optimization problems. So an optimization problem is when you have to maximize or minimize a quantity. So we'll see a bunch of them over the next couple days. Things like maximizing area, volume, profit, minimizing cost, distance, time. Okay, and it's going to be the question that will determine whether you're maximizing or whether you're minimizing. But in fact, the steps are always going to be the same. So our first example here, a study is conducted to test the effectiveness of a drug. The concentration of the drug in the bloodstream t hours after it is taken is given by the function c of t. And they want us to find when the maximum concentration occurs. Okay, so just like in the curve sketching unit, when we're trying to find the maximum point in a function, we start by taking the derivative, and then we're going to set that derivative equal to 0. Because we want to find where does the tangent have a horizontal slope. So to take the derivative of this, you could start right away by taking the derivative as it is, or you can multiply this 122 in if that helps you. Okay, so I'm going to start by doing that. And now I would take the derivative of this function. Okay, so I'm finding c prime of t. So taking the derivative of the e, it just stays exactly the same. And then we have to multiply by the derivative of the inside function, so the derivative of that exponent. And then the same thing here, we're taking the derivative of power e to the power, so it stays the same, we rewrite it. And then we multiply by the derivative of the exponent, which would just be a -1. Okay. And we can simplify this a little bit. Okay, so by multiplying those two coefficients together and the second two coefficients together, we get that c prime of t is equal to -2196 e to the power of -0.18t plus 122 times e to the power of -t. Okay, so now that we've taken the derivative, we are going to set that derivative equal to 0 and solve for where there's a maximum concentration. Okay, so now that it's set equal to 0, I'm going to move one of the terms over to the other side. Okay. And we are going to want to get all the numbers on one side and all the e terms on the other side. Okay, so we can divide both sides by the 122. Because that will cancel these out. Okay. And then similarly, I'm going to divide both sides by this e term. And that's because that will get rid of it on the other side. So it would cancel there. Okay, so on this side, we are left with 0.18, which is what that simplifies to. And on the other side, we have two terms dividing each other, but they have the same base, so we can just subtract the exponents. So when we do this, we're going to get e to the -t minus -0.18t, which ends up being -0.82t. So it does simplify fairly nicely there. Okay. And now we have one equation that has one t, so we need to isolate that t. And the way that we get a t out of an exponent position is we apply logarithms. Okay, and since our base is an e, I'm going to use ln, and I'm going to apply the ln to both sides. Okay, and that's going to work nicely with my base of e, since ln is log base e. Okay, so on this side, we're just left with the ln of 0.18. And on this side, we can pull down that exponent. And of course, the ln of e is 1, so it's going to go away. And now we can isolate t by dividing by this coefficient. Okay, and if we type that into our calculator to, let's say, 4 decimal places, we will get t equals 2.0912. So we haven't actually confirmed that that is a maximum yet, but that is the time that we get. Okay, so we do always have to verify that it's a maximum, and you can do that 2 ways. So just like in curve sketching, you can either test on either side of that t and see if it's changing from increasing to decreasing, or you can use the second derivative test. Okay, which way you do it's completely up to you. I'm gonna check the increasing versus decreasing. Okay, so I set up a little sign line where my boundary there is going to be this negative ln 0.18 over 0.82, which is really the 2.0912, just in exact form. And if we plugged 2 into our first derivative, since that's less than the 2.09, okay, we would get a positive, which means that it is increasing there. And if we plug 3 in of test value from the other side, okay, we would get a negative, which means it's decreasing. Therefore, our point is a maximum. Okay. And then we can make our concluding statement now that we have confirmed that it is actually a maximum. So the maximum concentration occurs at 2.0912 hours. And we just double check to make sure that that's answered our question, which was find when the maximum concentration occurs. And so we have in fact answered our question, and we are done. Okay, so we can move on to our next example now. So here's our next example. Okay, a boy is standing on a cliff and throws a stone into the air. There is a lake at the base of the vertical cliff. The height h in meters of the stone above the lake t seconds after it is thrown is given by the function h of t. With what velocity is the stone thrown? So we know that when we're dealing with velocity, that's going to be the first derivative of the height function. So it's going to be h prime of t because it's the change in height with respect to time. And if we're trying to find it when the stone is first thrown, then that's really its initial velocity, so that's going to be when time is 0. Okay, so we can start by finding our first derivative. It's a polynomial function, so it's a fairly quick derivative. We would get 30 minus 10t, and then we just plug in our 0. And we get 30, in this case, meters per second, because our height is in meters and our time is in seconds. Okay, so this is moving upwards since it's positive, and it's at that speed. So part B here is asking what is the velocity as the stone hits the lake? So once again, they're asking for velocity, so that's going to be our h prime at t. But when the stone hits the lake, so if we think about what this image looks like, he threw the stone, it goes up, and at some point it's going to come down, okay, and it will hit the lake. Graphically, that means we're really trying to find the t-intercept. Okay, so to find the t-intercept, we really want to find when is the height 0. So we are going to take h of t and we are going to set it equal to 0. And that's going to allow us to find the time, and then once we have the time, we will be able to find the velocity at that time. Okay, so you would try and factor this if you could, and if you can't factor it, you're going to then use the quadratic formula. So pause the video, take a minute, and do the quadratic formula. So if you do this, you would get that one of the times is negative, and of course we can't have a negative time. So we will omit that answer. Okay. And so we have this answer of 7.6690 seconds. So that would be the answer that we're going to use to find the velocity. So we want to find the velocity at that time. So we're going to plug in the negative 30 minus the square root of 2,180 over negative 10. And when we plug that into our first derivative, we get negative 46.6905. So for all word problems, we're going to write a therefore statement. So therefore, the velocity as the stone hits the lake is 46.6905 meters per second. And then because it's negative, that really means that the direction is down. So next they're asking us to find what is the acceleration of the stone at 2 seconds. So remember, acceleration, that is going to be the second derivative of the height function, because it's actually the rate of change of velocity. So if we take the derivative of h prime of t, we get negative 10, and the units would be meters per second squared. Okay. So because there's no variable in that, that actually means that the acceleration is going to be constant. So at 2 seconds, because it's always the same, then the acceleration is going to be negative 10 meters per second squared. Okay. And of course, if you've taken physics, in reality on Earth, the acceleration that would be due to gravity, which is what would be acting on the stone, would be closer to negative 9.8 meters per second squared. So our last question for this example is, when does the stone reach its maximum height? So this is optimization, once again, because we are maximizing it. And for optimization, we always take the derivative and we set it equal to 0 to figure out when it's reaching that maximum or sometimes minimum. So if we do that in this case, we already have the first derivative. So we're going to set it equal to 0. And we can solve for t. So t would be 3 in this case. We want to make sure that it is a maximum. And in this case, we don't actually need to do a test because our original function was a quadratic. Okay. And we know that when the quadratic has an a value that is negative, that means the parabola opens down. And has a maximum. Okay, so we can use what we know about parabolas to show that this function is definitely going to have a maximum height. Okay. Alternatively, you could do the first or second derivative test, but we do get our answer quicker by just knowing that it is a parabola and would have a maximum. So therefore, the stone reaches a maximum height at 3 seconds.